So today, once again, we'll learn the refrigeration cycle. So how exactly a refrigerator functions, how exactly a refrigerator or a water cooler function is what we'll understand, and how the working principle of it. When we talk about a refrigerator, it needs to have four important devices or components. So the components are basically a evaporator coils. Basically these are placed very near to the freezing compartment of a refrigerator. Condenser. A condenser is one which sheds the heat or rejects the heat from the refrigerant to the surrounding, which will be placed outside the refrigerator. Evaporator coils are one which absorbs heat from the refrigerated component or the freezing compartment, and then since the refrigerant absorbs the heat, so those are the ones which are provided in the freezing compartment. We need to have a expansion valve. What is expansion valve? Basically a device where suddenly a medium is expanded. What exactly happens when we do that? We have drop in pressure and drop in temperature, and that concept is used basically to cool the medium. So if you are talking about a refrigerator, you need to cool the medium which is kept inside the refrigerator. So for that reason we have an expansion valve. Sometimes capillary tubes are used, especially for a small refrigerator. For a larger refrigerator we use expansion valves. Okay. Then we need to have a compressor or a heat pump, or compressor or a pump. So in case of vapor compression refrigeration, we need to have compressor where you compress the fluid or the medium. Here the medium is refrigerant, and then we send it to the condenser. Here in case of vapor absorption, heat pump, there is a pump is used basically to force the fluid to other parts of the devices. So that's how we use these four components, especially in the refrigerator. Now first we'll understand what is a refrigerant. Now let's understand what is air here inside the room. It's a medium. What it does, it cools or heats the things which are kept here. The same way, especially the medium is used in refrigerator to absorb heat or reject heat from wherever it is required. Now it absorbs heat from the freezing compartment and rejects heat in the condenser. So that's the function of a refrigerant. Now more about it is not required here, but what are the different refrigerants used? Refrigerant 12, CCl carbon tetrachloride is being used, CO2 is being used as a gaseous refrigerant. We use ammonia for vapor absorption refrigeration. So different types of refrigerants are there. The technical name is R12, R22, R202, R134A, basically predominantly used in water coolers, 134A, and R22 in air conditioners, R12 in refrigerators. So these are the different types of, even for marine refrigerator we use R500. So these are the different types of refrigerant being used. So more are there, the properties of it are there in the data handbook, you can refer that. Okay. Now we'll understand the different types of refrigerator. There are two types of refrigerator. One is vapor compression and vapor absorption. So now we'll learn about vapor compression refrigeration system. Now we'll understand this cycle with the help of TS as well as TH diagram. So QH is heat rejected and QL is heat absorbed. Now, we will understand how exactly a vapor compression refrigeration system functions. So, as I said earlier, it needs to have 4 components: condenser, expansion valve, evaporator and compressor. Now, we will understand this device, what exactly, first I will explain here what exactly happens. So, the refrigerant, let us say it as R12, R134A or R22, which is passing from the evaporator coil, which has come out of the evaporator coil. So, at some pressure and temperature P1 and T1 and enters the compressor. So, what exactly happens for compressor, we need to provide work input, so W in, because it has to be supported with a prime mover, so work has to be supported. So, what exactly happens, the refrigerant enters the compressor, okay. So, refrigerant enters the compressor, so, and gets compressed. So, when it gets compressed, there is rise in temperature, you can see here, and rise in pressure from P1 to P2. So, from P1 to P2 in the TS diagram or in pH diagram, rise in pressure and rise in temperature. But you can see here the entropy remains constant. There is no change in entropy because of compression process. So, there is just rise in temperature and pressure, and that's what exactly happens. So, when there is rise in temperature, we need to shed heat because the refrigerant should go at a lower lower temperature. So, what we do, we condense the refrigerant to a lesser temperature. This happens at constant pressure. You can see 2 to 3 processes at constant pressure, and when it is compressed, naturally it gets temperature is more, so it will be superheated condition. Here you can see here, this is saturated vapor line, this is saturated liquid line, and this is region is superheated region. The refrigerant will be superheated. So, when you shed the heat in the condenser to the surrounding, there it will be. So, until when you do it, until it becomes, the refrigerant is completely super saturated liquid. So, saturated liquid, it should be saturated liquid, and then it passes through the expansion valve. What exactly happens in expansion valve? So, there is sudden expansion, there is drop in temperature from 3 to 4, you can see 3 to 4, and enthalpy remains constant because throttling process enthalpy is constant, okay. So, that's what exactly happens here, and we had drop in temperature. So, the pressure also drops down, so to less than atmospheric, basically here you can see less than atmospheric, so that the temperature is less than the evaporator chamber, so or the cold refrigerated space. So, the temperature of the refrigerant which enters will be somewhere around -4 to -10 degrees in ordinary refrigerator, and then when it enters the evaporator coils, so the refrigerator space will be somewhere around 0 degrees. It absorbs heat from 0 degrees. The refrigerant is at -10 degrees Celsius. So, naturally heat is transferred from the refrigerator space to the refrigerant. So, and then it passes out. It gets saturated. You can see here 4 to 1. It gets saturated vapor. When it absorbs heat, it gets vaporized, and it is at saturated vapor, and then once again it is sent to the compressor. You can see here that's what exactly happens. 4 to 1 is the constant pressure, but we are having evaporation taking place. There is increase, there is change of phase from liquid to vapor state because it absorbs heat. The refrigerant absorbs heat, and that's how basically your vapor compression refrigeration cycle functions. Is it clear? So, vapor compression, basically we use R12, R22, okay, R14, then R134A is also used. So, these are some of the different types of refrigerant which can be used here. So, this is what vapor compression refrigeration is. Now, please note here, when you are taking the value of 1, see here, when you are taking the value of 1, this line is at saturated vapor. So, H1 will be at Hg. What is Hg? this HF plus X into HFG, which is X is equal to 1. So HF plus HFG is Hg. So this will be Hg. So it is at saturated vapor. And H3 value, you can see here, H3 value will be at saturated liquid. So from the steam tables, whenever we are taking, so this is at P3, we need to take HF value for H3 to get the values from the steam tables for H3 or the refrigerant tables. And H1 value is Hg at P1. How do you calculate COP? Coefficient of performance for a refrigerator. It is QL, that is heat absorbed, okay, heat absorbed from the refrigerator space divided by W net, that is the work done to the compressor. So H1, QL is what? QL you can see here, H1 minus H4, and W net is H2 minus H1. So that's what it shows. And if you take what is the function of heat pump, what is the difference between a refrigerator and a heat pump? Both work on the same principles, but the objective, the end objective is different. Whereas in a refrigerator, we need to absorb heat from the refrigerator space and reject heat to the surrounding. Whereas in a heat pump, what we do, we absorb heat no doubt, but heating this space, the heating some space is what is the objective. So its function is to heat some space. Whereas in refrigerator, it should absorb heat and cool the place. So that's the difference here. So COP of heat pump is QH by W net. QH is what? So you can see here, QH is H2 minus H3, H2 minus H3, and W net is H2 minus H1. So that's it about the vapor compression refrigeration system. Now we will study whether reverse carnot cycle can be utilized for refrigeration system. Now we'll study about whether a reverse carnot cycle can be used as a refrigerator. So this is the reverse carnot cycle. So even for the refrigerator here, instead of expansion valve, we have a turbine to expand the refrigerant. Other things are the same. Evaporator, compressor, condenser are the same. The working principle is instead of expansion valve, we have a turbine, and that's the replacement here in this case. So in the turbine can expand the gases over the turbine blades, isn't it? So there will be drop in pressure, and once the exit temperature of the turbine is there, it will be less than the atmospheric, so the temperature will reduce drastically. Now we'll understand here whether process 2 to 3 is compression here. In the earlier case it was 1 to 2, 2 to 3 is compression process. So it is at constant entropy, 2 to 3. So temperature rises from 2 to 3 when we are compressing, and 3 to 4 is condenser, that is heat rejection in the condenser, 3 to 4, okay, heat rejection to the warm medium, and 4 to 1 is expansion in the turbine here, not the expansion valve or capillary tubes, and 1 to 2 is heat absorption process. Now we'll analyze whether this is possible. Yes, evaporation is possible at constant pressure. That is isothermal process. Temperature T1 and T2 are constant. So it's an isothermal process which happens in evaporation coils. It's quite possible. It's practically possible. But 3 to 4, once again, temperature remains constant. So what exactly happens? There is reduction in heat. So heat is lost. So but this process is once again possible, isothermal process, that's possible. So what we are doing, vapor state, bringing it to liquid state. The refrigerant will be in vapor state in condenser, bringing it to liquid state. So you are condensing the refrigerant, and that's what exactly happens in condenser. And we can maintain the same temperature, it's quite possible. But what is not possible here is 2 to 3 process compression. You can see here, here at this point, if you see, so it is at this point, if it is there, the refrigerant will be completely vapor. At this point, the refrigerant will be completely liquid. But in between, it is partially liquid. Here, more liquid and more vapor here. Am I right? So that's what will be the state of refrigerant at this point. So more of vapor and less of liquid, but compression of two phase, that is liquid phase and gaseous phase, is not possible. Compression of single phase, let it be liquid or exclusively gaseous state, it can be possible, but practically compression of liquid two phase is not possible, and that's why it fails. One more aspect is 4 to 1. Expansion of liquid in a turbine blades where moisture content will be very high. Maybe at this point you can see the refrigerant will be having 100% liquid phase and entering via the turbine blades, it damages the blades. So expansion through the turbine blades is practically not possible where the moisture content is high. In your steam turbines, you can see if it is less than 90% in any thermal power plant, the moisture content, that is the percentage of moisture content is less than 10%, then means more than 10%, it's not advisable. That is, dryness fraction should be more than 90, then we can use turbine for expansion process. Here in this case it is 100%. The entry of refrigerant is completely saturated liquid, then it expands, so it will be saturated liquid plus vapor. It's not quite feasible to have this, so it fails. Reverse Carnot cycle cannot be practically used for a refrigerator because of practical constraints. Now we'll solve a problem. Okay, can note down the problem. A refrigerator uses refrigerant. A refrigerator uses refrigerant 134A. So 134A is the refrigerant. We need to refer table 19 for saturated liquid state. That is, if it is at point 1, 3 and 4, we need to use table 19, your steam table, okay, or refrigerant table. And for H2 value, we need to refer table 20, because the refrigerant will be superheated. So a refrigerator uses refrigerant 134A, as the working fluid, and operates on an ideal vapor compression refrigeration cycle, between 0.14 and 0.8 megapascal. If the mass flow rate of the refrigerant is, that is m dot, is 0.05 kg per second, determine the rate of heat removal from the refrigerated space. Determine the rate of heat removal from the refrigerated space and the power input to the compressor. The rate of heat rejection to the environment. So the second part is the rate of heat rejection to the environment, that is QH, has to be calculated. Then COP of the refrigerator has to be calculated. So first, always write the TS diagram in this case. Always write a TS diagram to make you understand how exactly the problem is. So what is given? Refrigerant R134A. Then P1 is at 0.14 megapascal, or if you want it in bar, 1.4 bar. P2 at 0.8 megapascal, or 8 bar. M dot is 0.05 kg per second. Then what needs to be found out? QL, power, that is W net, QH and COP. These are the things which needs to be calculated. So before we start, this is required to be understood. So we need to buy this for your class. To refer this, basically for the problems on this data handbook is necessary. For in your exam SWE, this will be supplied by the college, whereas, or the department, whereas for your class work you need to procure this. So especially go to table 19. Table 18 is refrigerant R22. Okay, R12 is also there. Then R22 is also there. But what we require is R134A. That is table 19. You can see table 19 provides you what? Temperature, absolute pressure, density, volume, specific heat, entropy and enthalpy values you can get corresponding to the pressure. And table 20 gives you the values for superheated conditions, because P2 and T2 is at superheated temperature, T2. Basically the refrigerant at this point is superheated. So we need to take values for superheated values. So we need to refer that. Now considering this, okay, I'll refer the textbook values because I am solved using the textbook values. But here slightly it differs. You can take, but the answer will be the same because the difference of this will be what we require, and that will be saved. So what is P1? P1 is at 0.14 megapascal. So considering that H1 is what? Hg at 1.4 bar I have taken. S2 is equal to S1, okay, because S2 is equal to S1. So 0.8 and S2 is equal to S1. So H2 we get basically from the superheated values, table 20. So this will be kilojoules per kg. So refer table 20, go to 8 megapascal pressure on the top corresponding to S2 value. Okay, very near to that we need to take the H2 value, so which is given there, or you can, this is between two values, you can interpolate and get the exact answer for this. That's also possible. Now we know this. Then P3 value is what? P is equal to P2, which is 0.8 megapascal. Okay, so H3 is equal to Hf at 8 bar. Okay, so H3 is equal to 95.47 kilojoules per kg. Then once you know what is H3, we know H3 is equal to H4, which is 95.47 kilojoules per kg. Why? Because throttling process, H3 is equal to H4, expansion takes place, but throttling where enthalpy remains constant. So here. Now we'll solve the first problem, that is QL is m dot into, what is this? QL where exactly happens? H1 minus H4. So H1 minus H4. M dot is 0.05 kg per, or how much is it given? Kg per second into H1 is 239.16 minus H2 is, sorry, H4 is 95.47. This is in kilojoules per kg. So what we, kg gets cancelled, what remains is kilojoules per second. So we get this as 7.18 kilowatts. 7.18 kilowatts. The second part we need to calculate is W. W net is what? W net is m dot into H2 minus H1. So this is WL, isn't it? W in. Okay. So W in is m dot into H2 minus H1. So 0.05 kg per second, and H2 is how much? How much you are? 275. 275.39 minus of H1 is 239. So 239.16. So we get this as 1.81 kilowatts. Now what is as rate of heat rejection, QH, is m dot, where exactly happens? H2 minus H3, isn't it? So m dot into H2 minus H3. So H2 minus H3, QL, sorry, QH is H2 minus H3. So this will be 0.05. H2 is how much? 275. 275.39. H3 is 95.47. So you get this as 9 kilowatts. COP is QL by W net, that is 7.18 kilowatt divided by 1.81 kilowatt. We get this as 3.97 number. It is a number because kilowatts gets cancelled, so it's a number. So approximately around 4 is the COP. That's what we understand. So I'll just stop here. So that ends your refrigeration. Vapor absorption, just the theory part will be asked. Refer textbook and learn vapor absorption compression process. Only the theory, how exactly it functions. So instead of compressor, it will be a pump there, and how exactly functions you can read for yourself. So this completes your 5th unit. So more problems, I have given you notes during lockdown period, so you can refer those notes. Solved problems are given there, so you can refer those for your, based on this aspect it will be there. So just refer.